Let's explore the fascinating world of text analytics within natural language processing, or NLP. At its core, text analytics involves using artificial intelligence to extract meaningful information and insights from written language, transforming unstructured text into valuable data. This visual highlights four fundamental capabilities that enable computers to understand and work with text in powerful ways. As illustrated in the pinwheel diagram, these capabilities work together to provide a comprehensive understanding of text. We have sentiment analysis, which focuses on detecting the underlying emotion or opinion expressed, whether it's positive, negative, or neutral. Then there's key phrase identification, a technique used to automatically extract the most important topics or concepts discussed within a document. Complementing this is text summarization which aims to condense large volumes of text into shorter, coherent summaries while retaining the core information. Finally, conversational understanding enables systems to interpret and participate in human-like dialogue, powering applications like chatbots and virtual assistants. Technically speaking, natural language processing, NLP, is the broader field of AI concerned with the interaction between computers and human language. Text analytics is a specific application within NLP focused on analyzing text data. These processes often involve complex algorithms that can recognize patterns, understand grammar, context, and even nuances in language, much like humans do, but at a massive scale. The applications for these text analytics capabilities are vast and growing. Businesses use sentiment analysis to gauge customer satisfaction from reviews or social media. Key phrase identification helps researchers quickly understand the main themes in large datasets of articles. Text summarization assists in quickly digesting reports or news feeds, while conversational understanding is crucial for building effective customer service bots and voice assistants. In essence, these core text analytics functions, sentiment analysis, key phrase identification, text summarization, and conversational understanding, are essential tools. They allow us to unlock the wealth of information contained within text, enabling better decision-making, automation, and more natural interactions between humans and technology. Those powerful text analytics functions, understanding emotion, finding key phrases, summarizing content, and enabling conversation, all rely on processing language effectively. But before analysis can truly begin, raw, unstructured text must be transformed into a format computers can work with. This visual illuminates that crucial preparatory journey, text preparation for tokenization. It outlines the essential steps that convert messy human language into structured data suitable for algorithms. The process begins with raw text, the original unprocessed input. As shown in the diagram, this text first undergoes text normalization. This stage standardizes the content, typically involving actions like converting text to a consistent case, e.g., lowercase, removing punctuation, and handling special characters. Following normalization, stop word removal filters out high-frequency but low-meaning words, articles, prepositions, and conjunctions like the, is, in. This step helps focus the analysis on more significant terms. Next, the diagram illustrates n-gram formation. This technique groups adjacent words into sequences or n-grams like artificial intelligence as a bigram, helping capture multi-word concepts or phrases that hold specific meaning together. Subsequently, stemming reduces words to their root or base form. For example, running, ran, and runs might all be stemmed to run. While simpler than lemmatization, which considers vocabulary and morphological analysis, stemming effectively groups related word forms, further consolidating the text representation. These preparation steps are vital across countless applications. Search engines rely on tokenization and normalization to match queries effectively. Sentiment analysis and topic modeling algorithms perform more accurately when noise like stop words is removed and terms are standardized through stemming. Essentially, any task requiring a computer to understand or process text benefits immensely from this structured preparation, ensuring that subsequent analysis is both efficient and meaningful. In essence, text preparation for tokenization is the critical groundwork for unlocking insights from language data. By systematically cleaning, standardizing, and structuring raw text through normalization, stop-word removal, n-gram formation, and stemming, we create tokenized text, the refined input that empowers sophisticated natural language processing and text analytics models to function effectively. With our text meticulously prepared and tokenized, we unlock the potential for deeper understanding through various analytical methods. This visual introduces core text analysis techniques, represented as interconnected gears, signifying how these methods often work in concert to extract meaningful information. Each gear tooth represents a distinct but related process in making sense of textual data. At the heart of analysis lies the output of our previous steps, tokens. Tokenization, as shown, breaks text into manageable units, the essential input for other techniques. Building upon this, frequency analysis involves counting how often specific tokens appear within the text. This simple yet powerful technique helps identify the most discussed subjects or prominent terms. Directly related is the concept of stop words, common words like and, the, is, which are typically filtered out beforehand to ensure frequency analysis highlights truly significant terms, not just grammatical necessities. Moving beyond single words, techniques like bigrams, a specific type of n-gram, examine sequences of adjacent tokens, such as machine learning or customer support. Analyzing these pairs or sequences helps capture concepts that span multiple words, providing richer contextual understanding than individual word frequencies alone. Further refining our understanding of term importance is TF-IDF, which stands for Term Frequency Inverse Document Frequency. This statistical measure evaluates how relevant a word is to a document within a larger collection, giving higher weight to terms that are frequent in a specific document but rare across others. These techniques are the engine behind many AI applications. Search engines use frequency analysis and TF-IDF to rank results, while topic modeling relies heavily on identifying significant terms and phrases through these methods. Understanding customer feedback often involves analyzing bigrams and frequencies to pinpoint key issues or sentiments. Together, these interconnected techniques transform structured text data into valuable insights, forming the analytical core of services like Azure's language service. The analytical techniques that transform raw text into structured data, like word tokens and feature vectors, pave the way for intelligent automation. This visual introduces machine learning for text classification, a core capability that leverages this prepared data to automatically categorize text into predefined groups. At the center, we see the main process where machine learning models learn to perform this sorting task. The foundation, as depicted in the yellow tokenization block, remains crucial. Text must first be broken down into word tokens, which then undergo feature extraction, converting these tokens into numerical representations that algorithms can understand. This structured input feeds the central machine learning for text classification engine. This engine employs various classification algorithms, shown in blue, such as logistic regression or decision trees. These algorithms are trained on labeled examples to recognize patterns associated with different categories. One prominent application of text classification, highlighted in purple, is sentiment analysis. This involves automatically determining the emotional tone expressed within a piece of text, classifying it as positive sentiment, negative sentiment, or sometimes neutral. The machine learning model learns to associate certain words, phrases, and patterns identified through tokenization and feature extraction with specific sentiments based on the training data. Beyond sentiment, text classification powers numerous real-world applications. Think of email systems automatically filtering spam, customer support platforms routing inquiries to the correct department based on the described issue, or news aggregators categorizing articles by topic. Services like Azure Language Service provide pre-built and custom text classification models, enabling developers to integrate this powerful capability easily. In essence, text classification uses machine learning to bring order and understanding to vast amounts of unstructured text, turning raw words into actionable categories. While text classification effectively sorts information, truly understanding the meaning behind the words requires a deeper dive into semantics. This brings us to the sophisticated engines known as semantic language models, whose core components enable machines to grasp nuances in human language, moving beyond categorization to comprehension. At the foundation, as illustrated in the visual, lies token embeddings asterisk. This crucial step moves beyond simply identifying tokens. It represents them as numerical vectors within a complex, multi-dimensional space. Think of it like a detailed map where words or tokens with similar meanings are positioned closer together. This spatial representation captures the semantic relationships between words, forming the bedrock for understanding context and meaning, a significant advance from basic feature extraction. These rich vector representations fuel a wide array of NLP tasks As the visual indicates, this includes capabilities like text analysis, which encompasses the classification tasks discussed previously, but also extends to more complex functions like machine translation and question answering, all relying on the model's understanding of meaning. To effectively perform these tasks and capture the subtleties of language, significant model complexity is inherent. These models operate within those high-dimensional vector spaces, processing intricate patterns and relationships far beyond simple keyword matching. Services like the Azure AI Language Service sit atop this stack, packaging these advanced language model capabilities. This accessibility empowers developers to integrate sophisticated semantic understanding into applications ranging from intelligent chatbots and accurate machine translation services to nuanced sentiment analysis and automatic text summarization, effectively leveraging the model's grasp of meaning without needing to build these complex systems from scratch. In essence, semantic language models represent a powerful evolution in AI. By building layer upon layer, from token embeddings capturing meaning through complex model architectures to enabling diverse NLP tasks, they unlock a deeper level of language comprehension. Platforms like Azure AI Language Service make this sophisticated technology readily available, driving innovation in how applications interact with and understand human language. That sophisticated understanding, accessible via platforms like the Azure AI Language Service, unlocks a suite of powerful text analysis features, as illustrated here. This service acts as the central engine, branching out to provide specific tools for dissecting and comprehending unstructured text, transforming raw words into actionable insights. The visual highlights several key capabilities radiating from the core Azure AI Language Service. Foundational features include language detection which automatically identifies the language of a given text, providing a language code essential for subsequent processing. We then move to identifying specific details with named entity recognition which pinpoints mentions of people, places, events, and other predefined categories. Entity linking complements this by connecting these entities to entries in a knowledge base like Wikipedia, adding valuable context. For understanding the core subject matter, key phrase extraction pulls out the main talking points or concepts. Further enhancing comprehension, summarization condenses large documents into shorter versions containing the most important information. Gauging the underlying feeling or opinion expressed is the role of sentiment analysis classifying text typically as positive or negative. Crucially, in today's data-sensitive world, PII detection identifies personally identifiable information, such as personal health details or other sensitive data, enabling compliance and privacy protection. Each of these features relies on sophisticated models trained to recognize complex patterns within the text. These features have broad real-world applications. Sentiment analysis helps businesses track customer satisfaction from reviews or social media. NER and key phrase extraction power intelligent search and knowledge discovery systems. Summarization allows users to quickly grasp the essence of lengthy reports or articles, while PII detection is vital for moderating content and ensuring data security in applications handling user information. In summary, the Azure AI Language Service offers a versatile array of text analysis tools. From identifying the language and key entities to understanding sentiment and summarizing content, these features provide developers with the building blocks needed to create applications that can truly interact with and understand human language on a deeper level. While the Azure AI Language Service provides a broad toolkit, let's zoom in on one particularly powerful capability mentioned earlier, named Entity Recognition, or NER. This feature acts like an intelligent scanner, automatically locating and classifying specific pieces of information, the entities hidden within blocks of unstructured text, bringing structure to the chaos of raw language. This visual breaks down the common types of entities that Azure AI Language can recognize. At the heart are the recognized entities themselves. Radiating outwards, we see the distinct categories the service identifies. It can pinpoint persons recognizing the names of individuals or groups. It identifies geographical places as locations and detects companies or institutions under the organization category. These three represent some of the most common proper nouns we seek in text. Beyond proper nouns, NER extends to other crucial data types. It measures numerical values or ranges, classifying them as quantity asterisk. It interprets temporal expressions, understanding mentions of dates and times as date time ***. Furthermore, it identifies links to web resources, categorizing them as **URL. Each category represents a specific type of information extracted from the text. The underlying technology uses sophisticated machine learning models. These models are trained on vast amounts of text to learn the patterns and contexts that signal the presence of a specific entity type. For example, it learns that Microsoft often appears in contexts related to company's organization, while Seattle typically refers to a place location, and next Tuesday at 3 p.m. signifies a date and time date time. This capability is incredibly useful in the real world. Businesses can use NER to quickly extract competitor names or product mentions from articles. Legal teams might use it to find specific dates or locations in contracts. It allows applications to automatically populate databases, categorize documents based on mentioned entities, or enhance search results by identifying key information within the text, ultimately making unstructured data far more accessible and actionable. Just as named entity recognition helps us extract specific details from text, understanding the language of that text is a fundamental prerequisite for many AI tasks. However, identifying the language isn't always a simple task, especially when dealing with diverse real-world data. This visual presents two distinct scenarios and the corresponding approaches within Azure AI Language for tackling language detection challenges. On one side, we have clear language detection ***. This approach, represented by the green panel and the magnifying glass icon signifying focus, is ideal when the input text is predominantly in a single, identifiable language. Think of standard documents, articles, or longer user comments. Here, the service can confidently utilize the strong signals of the predominant language to deliver highly accurate results, confidently pinpointing the language used. Contrast this with the challenge of ambiguous language detection shown in the orange panel with the cloud and question mark icon representing uncertainty. This scenario arises when text contains a mix of languages. Perhaps a user switches between Spanish and English in a single message, or when the text is very short, fragmented, or contains jargon, making definitive identification difficult. The goal here is to effectively handle these mixed or unclear inputs, providing the best possible identification despite the ambiguity. Choosing the right approach depends entirely on the nature of the text you expect to process. For analyzing formal reports, clear language detection is likely sufficient. But for processing social media feeds, chatbot interactions, or international customer reviews where language mixing is common, leveraging capabilities designed for ambiguous situations becomes crucial. Selecting the appropriate method ensures that downstream tasks like translation, sentiment analysis, or even the named entity recognition we discussed previously operate on accurately identified language data, leading to more reliable and meaningful insights. Beyond simply knowing what language is being used, Azure AI Language empowers us to understand the feeling conveyed within the text. This crucial capability is known as sentiment analysis, visually represented here as a way to categorize customer feedback based on the emotional tone expressed. It's about moving from language identification to emotional interpretation. This visual breaks down sentiment into 4 key categories, arranged in a helpful matrix. In the upper quadrants, we see high-intensity emotions. Quadrant 1, marked in red with a downcast icon, signifies a highly negative review, indicating extreme dissatisfaction. Conversely, Quadrant 2, in bright green with a positive group icon, represents a highly positive review, showing strong approval and high positivity. The lower quadrants deal with milder feelings. Quadrant 3, in orange with a thumbs-down icon, points to mildly negative reviews, slight dissatisfaction. Finally, Quadrant 4, in lighter green with celebratory icons, denotes mildly positive reviews, reflecting gentle approval or low positivity. Technically, sentiment analysis involves using natural language processing and machine learning techniques to analyze text and assign a sentiment score. This score typically indicates polarity, whether the text is positive, negative, or neutral, and often includes a measure of confidence or intensity, aligning with the highly versus mildly distinction shown here. Azure AI Language Service provides pre-built models to perform this analysis automatically on input text. The applications for sentiment analysis are vast and impactful. Businesses use it extensively to gauge customer satisfaction from reviews, survey responses, and support tickets. It's invaluable for monitoring brand perception on social media, tracking reactions to marketing campaigns, and identifying areas for product or service improvement. Understanding the collective sentiment allows organizations to make data-driven decisions and respond proactively to customer needs and opinions. In essence, sentiment analysis transforms raw text into actionable emotional insights. By classifying opinions, as illustrated in these 4 quadrants, Azure AI Language helps us understand not just what people are saying, but how they feel, providing a deeper layer of understanding critical for communication and strategy. While knowing the feeling behind customer feedback is vital, as we saw with sentiment analysis, understanding the specific subjects being discussed is equally important. This visual introduces key phrase extraction, another powerful feature of Azure AI Language designed to pinpoint the main topics within a text, illustrated here through the lens of analyzing restaurant reviews. Imagine sifting through numerous reviews. Key phrase extraction acts like an intelligent highlighter, automatically pulling out the most significant terms. The diagram shows a central document icon representing a review surrounded by orbiting icons and text. These orbiting elements are the key phrases identified by the service. We see terms like great food, focusing specifically on cuisine quality, friendly hostess, and attentive service, highlighting aspects of customer interaction and ambience, describing the restaurant's environment. Other phrases like birthday celebration capture the occasion, while fantastic experience summarizes an overall positive sentiment linked to these specific points. It essentially distills the review down to its core components. Technically, key phrase extraction employs natural language processing algorithms to scan text and identify noun phrases or keywords that represent the main concepts. Unlike just listing common words, it focuses on terms that carry significant meaning within the context of the document. Azure AI Language provides this capability, allowing developers to integrate automated topic identification into their applications without needing deep expertise in linguistics or machine learning model training. The applications are diverse. Businesses can use key phrase extraction to quickly grasp the main themes in large volumes of customer feedback, survey responses, or social media comments. It aids in categorizing support requests, identifying trending topics in news feeds, summarizing lengthy documents, and even enhancing search engine capabilities by focusing on the most relevant terms within content. It helps cut through the noise to find the signal. In essence, key phrase extraction moves beyond the asterisk how asterisk sentiment to reveal the asterisk what. By automatically identifying the crucial topics like food, service, or ambience within text, Azure AI Language provides a structured way to understand content at scale, complementing sentiment analysis for a comprehensive view of textual data.